Rainfall is one of the hardest physical fields to measure. Why? Because it is spatially localized, highly intermittent, and convective storms create sharp gradients over just a few kilometers. No single instrument captures it all. Rain gauges give you precise point measurements. Commercial microwave links give you path-integrated averages along communication towers. And weather radar or satellite products give you aerial averages over regular grid cells. Each sensor observes the exact same atmospheric process, but through a completely different spatial geometry. The problem is that most modern fusion methods treat these sensors as interchangeable data channels, completely ignoring the fact that a point measurement, a line integral, and a grid cell impose fundamentally different geometric constraints on the underlying field. Today, we are breaking down a new approach that fixes this by building a geometry-aware, multi-support heterogeneous graph neural network that actually respects the shape of how each sensor measures the world. Classical interpolation methods like inverse distance weighting or kriging rely on assumptions of spatial stationarity and Gaussian statistics. But convective rainfall is highly nonlinear and localized, so those assumptions routinely break down. Recent learning-based approaches, including convolutional networks and standard graph neural networks, relax those statistical assumptions, but they still handle sensor heterogeneity in feature space. In a typical graph model, a gauge, a microwave link, and a radar pixel are just different node types or feature vectors. The geometry of the measurement itself is discarded. If you collapse a microwave link down to a single midpoint coordinate, you lose the fact that the sensor actually integrates rainfall along a 2-kilometer span. That geometric information is exactly what you need to reconstruct fine-scale rainfall fields, and it is what this paper explicitly models. The proposed framework introduces a multi-support heterogeneous graph neural network where observations are organized into distinct support-typed layers: zero-dimensional point nodes for gauges, one-dimensional line nodes for microwave links, and two-dimensional grid nodes for radar or satellite products. Instead of treating them as generic nodes, the graph construction preserves their measurement geometry. For the zero-dimensional layer, gauge nodes are placed at their exact coordinates, and target prediction nodes are masked during training. For the one-dimensional layer, a microwave link is not collapsed to a proxy point. It is represented by two endpoint nodes connected by a within-support edge, with a physical path length baked into the edge weight. The two-dimensional layer works similarly, with grid cells linked to their 8 spatial neighbors. The architectural innovation here is the cross-support edge construction. Every observation layer connects to a central point support prediction layer, but the connectivity rules respect the underlying geometry. For gridded sources, prediction nodes connect to their nearest grid cells using a Haversine distance metric. For line-supported sensors, connectivity is not based on point-to-point proximity. Instead, the system calculates the perpendicular distance from a prediction node to the actual line segment of the microwave link. The prediction node then connects to both endpoints of that link, weighted by their respective distances. This means the model receives a separate, geometrically appropriate message from each end of the integration path, preserving the line support instead of averaging it into a single point. Once the graph is built, information flows through a heterogeneous convolution. Each edge type gets its own learned weight matrix, so the model can learn to weigh point, line, and grid inputs differently. Messages are aggregated via a mean operation and pass through RayLU activations across multiple layers. Because each edge type has distinct parameters, the architecture naturally handles varying support compositions without breaking. But there is a critical training challenge. If you feed a node its own observation and ask it to predict itself, the model will just learn an identity mapping. It will copy the input to the output and never learn any spatial relationships. To prevent this, the authors use an inductive mask node formulation. At each training step, a single point support node has its observation masked to 0, and the model must predict that value using only messages from its neighbors. Crucially, the node's structural identity, like its Laplacian positional encoding, is preserved. Only the raw measurement and a validity flag are masked. This forces the network to actually learn spatial dependencies. At inference, you can insert a regular grid of virtual target nodes, connect them using the same cross-support rules, and run a single forward pass to reconstruct the field at any user-defined resolution. The prediction resolution is completely decoupled from the input sensor resolution. The authors tested this on 2 distinct testbeds, Singapore and Sydney. In Singapore, they fused 70 rain gauges, 414 commercial microwave links, and 1-kilometer resolution radar data. The geometry-aware multi-support model reduced the root mean square error by 23% compared to inverse distance weighting, and it consistently outperformed both convolutional fusion baselines and a support-agnostic graph neural network. The support-agnostic baseline is a key control. It uses the exact same architecture and data, but treats every observation as a zero-dimensional point connected by plane distance edges. It only recovered about half the improvement, proving that the gain comes from explicitly modeling support geometry, not just from using a graph structure. But here is where it gets really interesting. When they applied the exact same framework to Sydney, using gauges and 2 gridded sources, the model actually performed worse than classical interpolation. The gauge-only graph model did not beat inverse distance weighting, and adding radar or satellite data did not help. Rather than treating this as a failure, the authors dug into the spatial statistics and found a unifying mechanism. The skill of multi-support fusion depends entirely on the gauge spacing relative to the spatial correlation length of the rainfall field. In Sydney, the gauge network is dense enough that the field is already well resolved. The rainfall decorrelates slowly over several kilometers, so nearby gauges already provide a highly accurate estimate. There is almost no residual subgauge structure left for a learned model or additional sensors to recover. In Singapore, convective rainfall decorrelates much faster. The field is undersampled relative to its correlation length, leaving significant subgauge structure that fixed interpolation misses. That is where the geometry-aware fusion shines. Radar provides structural cues, microwave links bridge the gaps between gauges, and the graph correctly routes that information without collapsing the geometry. This paper makes a compelling case that, when fusing heterogeneous spatial data, the geometry of the measurement is just as important as the data itself. By representing point, line, and grid observations as distinct support layers and routing information through geometry-aware cross-support edges, the model extracts significantly more skill from the same inputs. The framework is also highly modular and inductive, meaning you can drop in new sensor types or query the field at arbitrary resolutions without retraining. While the correlation length analysis is specific to these two testbeds, the underlying principle applies broadly to any multi-support estimation problem, from environmental monitoring to infrastructure sensing. If you are working with heterogeneous spatial data, and your current fusion pipeline is treating everything as a flat feature vector, it might be time to let the geometry do the heavy lifting. The full code and models are open-sourced, so I will link the paper and repository in the description. Let me know in the comments how you are handling multi-source spatial fusion in your own work, and thanks for watching.